Hello and welcome to the online class for our first chapter. As you can see, our first chapter is entitled Integration. Actually, it's more something like Lebesgue integration. So you're going to learn soon why it's called Lebesgue integration. And that's the usual one. And actually, what we're going to talk about is parameter-dependent integrals and the big theorems that are related to that. Why are we beginning with this? Because it's the foundations are a lot of things that are coming next. We're going to see Fourier series, we're going to see Fourier transform, we're going to see Laplace transform this year. So these are all parameter-dependent integrals. So we should have a proper theoretical setting to study this. Okay, so let's see. So this is what we're planning to do. There are 4 sections actually to this chapter. The first 2 are going to be rather quick, so it's going to be for today. We're going to see why there was a need for a new integration theory and how it is constructed, talking about measure theory quickly, and a very important notion, which is the almost everywhere notion that is a novelty for us in math. And then we will see how we can correctly build an integral, but you will see that it looks a lot like the one you used to practice in the previous years. And then there's going to be the third section where we really have those very important theorems. So, well, actually, there are only 3 important theorems, but first one is going to be have some corollary and some few application extensions. Second one, the Lebesgue dominated convergence theorem, is the most important one actually, and it's going to be the one that you can interpret as a parameter-dependent integral theorem to decide for continuity and differentiability. Right, and then finally we'll have a fourth section about some specific functional spaces and a new idea which is called convolution. All right, but for today we are planning to go over sections 1, 2, and I think we should have enough time to go over the Bepo-Levy monotone convergence theorem. So let's see. All right. So why would we need a new theory of integration? Just a bit of setting of historical setting. Since antiquity, people have been dealing with the need to calculate areas, volumes, surfaces, and things like this. So you know that there's a lot of geometrical use for that, geometrical means to do these calculations. But then during the 16th century, 16th and 17th century, calculus began to be developed by Descartes, Galileo, Newton, Leibniz. Leibniz was actually the first one to introduce the integral as the reverse process to integration. Right, so this is all the kind of math you've been studying at the end of since the end of high school and well, even probably previously with the introduction of functions, but then we've been doing quite a lot of calculus in the first 2 years of your engineering studies. You will see when you want to inquire about the real theory of integration that well, we needed some different theories for different needs. The one you've been dealing with is the Riemann integration tool. He was developed by Riemann in the 1854, expanding the work of Cauchy. So that's the usual integral that you've been dealing with. We will see that it's defining as the approximation by sums of rectangles, but you've seen that many times. And Lebesgue actually found the need for a new kind of integration. That was about 50 years later, because of many things. At that time, there was some new physics that was going to be developed. It was the beginning of thinking about quantum mechanics that would be really theoretized a few years later, but there were a lot of questions about measures. And of course, if you relate integration to measuring, you will need to be much more rigorous regarding the measuring tools that you have. So this is basically what Lebesgue did. Um, so the new physics that was being developed needed more rigor. That was the beginning of the development of quantum mechanics, and also in parallel, the need for a solid probability theory. And all this led to this idea of measure and the measure theory. And we will talk about this quickly. We will talk about something very important that is the indicator function and maybe the Dirac function, which is a kind of generalized function, and the almost everywhere notion. Okay. So just the guys that are involved here. So Riemann, the one who developed your own theory of integration that you've been manipulating since high school. Emile Borel, he was the one who developed the measure theory. And in his steps came Henri Lebesgue, who did this Lebesgue integral that we are going to study now. Right, so let's see what we know, what we've been doing with integration in the last few years for you.